Hello everyone, in the previous two classes, we studied two types of rate of change problems. In question 1, the instantaneous speed is the limit of the average speed as delta t approaches zero infinitely. In the second question, the tangent slope is the limit of the secant slope as delta x approaches zero infinitely. When addressing these two issues, have we identified any commonalities between them? In question 1, average velocity represents the average rate of change of height over time, while instantaneous velocity denotes the instantaneous rate of change of height with respect to time. In question 2, the secant slope signifies the average rate of change of the ordinate of a point on the parabola with respect to the abscissa. The tangent slope, on the other hand, signifies the instantaneous rate of change of the ordinate of a point on the parabola with respect to the abscissa. Although these two types of problems originate from different disciplines, they both employ the method of approximating the instantaneous rate of change with the average rate of change. As we all know, a function is a mathematical model that depicts the movement and changes in the real world. In question 1, the height is a function of time t. In question 2, the vertical coordinate of a point on the parabola is a function of the horizontal coordinate. Both problems investigate the rate of change of the function value with respect to the independent variable. So, for a general function y equals fx, can you use the idea of approximating the instantaneous rate of change with the average rate of change to study its instantaneous rate of change at a certain point, such as when x equals x0? Let's first represent the average rate of change. To study the instantaneous rate of change of the function y equals to fx at the point where x equals x0, we can investigate the range within which the average rate of change of the function value occurs. In question 1, to study the instantaneous velocity of the athlete at time t equals 1, we selected a time increment delta t. We first calculated the average rate of change of height with time between the moment t equals 1 and the moment t equals 1 plus delta t. In question 2, to find the tangent slope of the curve at the point 1, we selected a change amount delta x for the independent variable x. We first calculated the average rate of change of the function value with respect to the independent variable when x is between 1 and 1 plus delta x. To study the instantaneous rate of change of the function y equals to fx at the point where x equals x0, we can select a change amount delta x for the independent variable x. Here, delta x can be either positive or negative, but not zero. We calculate the average rate of change of the function value during the process where the independent variable x changes from x0 to x0 plus delta x. So, how should this average rate of change be expressed? In question 1, the average speed, which represents the average rate of change of height over time, is calculated by dividing the change in height by the change in time. In question 2, the slope of the secant line, which represents the average rate of change of the ordinate of a point on the parabola, is determined by dividing the change in the function value by the change in the independent variable. Generally, for a function y equals to fx, we can calculate the average rate of change by dividing the change in the function value by the change in the independent variable. The independent variable x changes from x0 to x0 plus delta x. Correspondingly, the function value y changes from fx0 to fx0 plus delta x. In this process, the change in the independent variable is the change in the function value by delta x, and delta y is equal to fx0 plus delta x minus fx0. The ratio delta y to delta x, which is the difference between fx0 plus delta x minus fx0 divided by delta, represents the average rate of change of the function y equals to fx from x0 to x0 plus delta x. Having obtained the average rate of change, how can we represent the instantaneous rate of change? Let's review the two previous questions. In problem 1, regardless of whether delta t is less than or greater than 0, when delta t approaches 0 infinitely, the average velocity v bar approaches a certain negative value of 5 infinitely. Therefore, negative 5 is the instantaneous velocity of the athlete when t equals 1 moment. In problem 2, regardless of whether delta x is less than or greater than 0, when delta x approaches 0 infinitely, the slope k of the tangent line approaches a certain value of 2 infinitely. Therefore, 2 is the slope of the tangent line at another point on the parabola. So generally, for the function y equal to fx, regardless of whether delta x is less than or greater than 0, when delta x approaches 0 infinitely, both x0 and delta x approach x0 infinitely. If the average rate of change delta y can infinitely approach a certain value compared to delta x, as in the previous two problems, then this value is the instantaneous rate of change of the function at x equals to x0. So, when delta x approaches 0 infinitely, will the average rate of change delta y necessarily approach a certain value infinitely compared to delta x? Everyone can try giving counter-examples. For example, if the function fx is equal to the absolute value of x, we examine its variation around x equals to 0. We first calculate the average rate of change of the delta x function value from 0 to 0. Since f delta x is the absolute value of delta x, f0 is equal to 0. Therefore, the average rate of change delta y is equal to the ratio of the absolute value of delta x to delta x. When delta x is less than 0, the absolute value of delta x is equal to negative delta x, so the average rate of change is always equal to negative 1. When delta x is greater than 0, the absolute value of delta x is equal to delta x, so the average rate of change is always equal to 1. We find that when delta x approaches 0 infinitely from both the negative and positive sides, the average rate of change does not approach the same definite value infinitely. This indicates that when delta x approaches 0 infinitely, the average rate of change, delta y, may not necessarily approach a certain value infinitely as delta x does. If as delta x approaches 0 infinitely, the average rate of change, delta y, approaches a certain value infinitely more than delta x, that is, delta y has a limit compared to x, we say that y equals fx is differentiable at x equals x0, and this certain value is called the derivative of y equals fx at x equals x0, also known as the instantaneous rate of change. There are two ways to denote it. If we use the symbol of limit to represent this definition, then y equals fx, and the derivative at x equals x0 is equal to the average rate of change. Delta y compared to delta x, the limit when delta x approaches 0 infinitely. That is, when delta x approaches 0 infinitely, the limit of the ratio of the difference between fx0 plus delta x minus fx0 to delta x. From the definition of the derivative, it can be seen that the derivative is the limit of the average rate of change and is the mathematical expression of the instantaneous rate of change. Based on the definition of derivative, can you use derivatives to restate the conclusions of the speed problem of a diver and the tangent problem of a parabola? The instantaneous velocity of a diver at time t equals 1 is the derivative value of its height hd at time t equals 1. The slope of the tangent line of a parabola at point 1 is the derivative value of the function y equals fx at x equals 1. In fact, derivatives can describe the instantaneous rate of change of many things that are in motion, such as efficiency, the growth rate of gross domestic product, and so on. Given the powerful function of derivatives, we need to be able to calculate the derivative value at a given point for a specific function. Let's take a look at example 1. Let fx be equal to 1 of x and find the derivative of the function fx at x equals to 1. For the study of derivatives, currently we only have the tool of defining them. We require the function y to be equal to fx, and for the derivative at x to be equal to 1, we only need to set the value of x0 in the formula to 1. For ease of calculation, we can first calculate the ratio of the average rate of change delta y to delta x, and then take its limit. Since f1 plus delta x equals 1 plus delta x divided by 1, f1 equals 1. We simplify it by substituting and obtain the average rate of change. Delta y is equal to negative 1 plus 1/2 of delta x. Next, we take the limit of the average rate of change to obtain the derivative of y equals to fx at x equals to 1, which is the limit of the above equation when delta x approaches 0 infinitely. When delta x approaches 0 infinitely, adding 1 to delta x leads to an infinite approach to 1, and its negative reciprocal leads to an infinite approach to negative 1. Therefore, the derivative of fx at x equals to 1 is equal to negative 1. Looking back at the solution process of example 1, can you summarize the steps for finding the derivative of the function y equal to fx at x equal to x0? We can divide it into two steps. The first step is to write the function y as the average rate of change of fx from x0 to x0 plus delta x, where delta y is simplified to delta x. The second step is to calculate the average rate of change, which is the limit when delta x approaches 0 infinitely. If this limit exists, then the function y equals fx, and the derivative at x equals x0 is this limit value. Next, we will apply the concept of derivatives to solve several practical problems. Refining crude oil into various products such as gasoline, diesel, plastics, etc., requires cooling and heating of the crude oil. It is known that at the xth hour, the temperature of crude oil is Y, which is equal to Fx, which is x squared minus 7x plus 15, where x is less than or equal to 8 and greater than or equal to 0. Calculate the instantaneous rate of change in crude oil temperature at the 2nd and 6th hour and explain their significance. This is a practical problem. What does it have to do with derivatives? Through our previous studies, we all know that derivatives are mathematical expressions of instantaneous rates of change. Therefore, at the 2nd hour, the instantaneous rate of change in crude oil temperature is the derivative of the crude oil temperature Fx at x equals to 2. At the 6th hour, the instantaneous rate of change in crude oil temperature is the derivative of crude oil temperature Fx at x equals to 6. We calculate the derivative of the function y equals to fx at x equals to 2 based on the definition of derivatives and the steps we summarized earlier. We need to calculate the average rate of change of the function fx from 2 to 2 plus delta x. We substitute 2 and 2 plus delta x into the analytical formula of function fx and organize them, and we can obtain that the average rate of change delta y is equal to delta x minus 3 when compared to delta x. Next, we will take the limit on it. The derivative of y equal to fx at x equal to 2 is equal to the limit of the difference between delta x and 3 when delta x approaches 0 infinitely. When delta x approaches 0 infinitely, delta x decreases by 3 and approaches negative 3 infinitely. Therefore, the derivative of y equals to fx at x equals to 2 is negative 3. Similarly, we can calculate that the derivative of fx6 is equal to 5. Please complete the specific calculation process after class. The function y is equal to fx, and the derivative at x equals to 2 is negative 3, and the derivative at x equals to 6 is 5. What is the significance of this practical problem? We all know that derivatives are mathematical representations of instantaneous rates of change. In this question, y equals fx, and the derivative at x equals x0 is the instantaneous rate of change of crude oil temperature at time x0. It reflects the variation of crude oil temperature around time x0. Specifically, the derivative of fx at 2 is negative 3, indicating that the instantaneous rate of change in crude oil temperature at hour 2 is negative 3 degrees per hour. This suggests that around hour 2, the crude oil temperature decreases at a rate of approximately 3 degrees per hour. The derivative here, that is, the instantaneous rate of change, is negative, reflecting a decreasing trend of change. The derivative of fx at 6 is equal to 5, indicating that at the 6th hour, the instantaneous rate of change in crude oil temperature is 5 degrees per hour. This suggests that around the 6th hour, the crude oil temperature is rising at a rate of approximately 5 degrees per hour. Here, the derivative or instantaneous rate of change is positive, reflecting an upward trend of change. Let's take another look at a practical problem. A car is traveling in a straight line on a highway with variable speed. Assuming the speed of the car at t seconds, y is equal to vt, negative t squared plus 6t plus 60. Calculate the instantaneous acceleration of the car at the 2nd and 6th seconds, and explain their significance. This question involves the concepts of velocity and instantaneous acceleration in physics. Do you know the relationship between speed and instantaneous acceleration? According to physics knowledge, instantaneous acceleration is the instantaneous rate of change of velocity. Therefore, the instantaneous acceleration of the car at the 2nd second is the derivative of the velocity vt at t equals to 2. The instantaneous acceleration at the 6th second is the derivative of the velocity vt at t equals to 6. Based on the definition of derivatives and following the steps summarized earlier, we will first calculate the instantaneous acceleration of the car at the 2nd second. Firstly, we need to calculate the average rate of change of velocity, vt, between t equals to 2 and t equals to 2 plus delta t. We incorporate 2 and 2 plus delta t into the analytical formula of vt. By sorting it out, delta y is equal to delta t minus delta t plus 2. Next, we can take the limit to obtain the derivative value at vt equals 2, which is equal to the limit of negative delta t plus 2 when delta t approaches 0 infinitely. When delta t approaches 0 infinitely, negative delta t also approaches 0 infinitely, and adding 2 leads to an infinite approach to 2. Therefore, the derivative of vt at 2 is equal to 2. Similarly, we can calculate that the derivative of vt at 6 is negative 6. What is the significance of the derivative of Vt at t equal to 2 and t equal to 6 in this practical problem? In this question, the derivative of Vt at t equals t0 is the instantaneous acceleration of the car at t0, reflecting the variation of velocity near t0. Specifically, the derivative of Vt at 2 is equal to 2, indicating that the instantaneous acceleration of the car at the second is 2 meters per second squared. This indicates that around the second, the speed of the car increases by approximately 2 meters per second. The derivative or instantaneous rate of change is positive, reflecting an increasing trend of change. The derivative of Vt at 6 is negative 6, indicating that at the second, the instantaneous acceleration of the car is negative 6 meters per second squared. This suggests that around the second, the speed of the car decreases by approximately 6 meters per second. The derivative or instantaneous rate of change here is negative, reflecting a decreasing trend of change. Instantaneous velocity is the instantaneous rate of change of displacement, and instantaneous acceleration is the instantaneous rate of change of velocity. According to the function of distance with respect to time, finding velocity and acceleration is a fundamental problem, which, along with finding the tangent of a known curve, directly leads to the generation of derivatives. Newton and Leibniz, two famous mathematicians, started with these two problems and pioneered calculus. Finally, let's summarize today's class. Let's start with the two types of rate of change issues discussed in the previous two classes. The concept of derivative was derived by summarizing the commonalities between these two types of rate of change problems. We have summarized the steps of finding the derivative of a given function at a certain point according to the definition, and applied the meaning of the derivative to analyze and explain practical problems. The concept of derivative is relatively abstract. It is a mathematical expression of instantaneous rate of change, which contains the viewpoint of motion change and the idea of using the average rate of change to approximate the limit of instantaneous rate of change. That's all for today's class. Goodbye.